Yeah, the next hands-on session is going to be by Erin Liddell. So she is a chief scientist at H2O, and yeah, knows everything about how to wrangle data in practice, and also how to use AutoML for it, and when to maybe not use AutoML and so on. So yeah, please join me in welcoming Erin. You.
Thanks. Thank you, everybody. Sorry I couldn't be there in person this year. In an ironic event, set of events, I actually got COVID last week, so I was trying to avoid that and didn't. Okay, so I put a link into the chat. So basically, this is a hands-on workshop, so I really want to focus on just code, and I didn't actually prepare any slides. I could maybe, if we have time at the end, go through some slides, but really it's just going to be going through some notebooks in Python, and then hopefully this will be also quite interactive. I don't know to what capacity people can ask questions. If you're logged into Zoom, I suppose you can. I think most people are just watching from the classroom. So if there's some way that you guys can ask questions, maybe in the chat, or if there's a microphone or something like that, feel free to do that at any time. So I'll just give you guys a minute to, yeah.
So everybody is watching live. Nobody's logged into Zoom.
Okay.
We have one person in Zoom that's the Hannover side, and but we have mics here, so people can ask questions.
Okay. Right. Yeah. Sorry, I forgot chat is associated with Zoom, so you can't do that either. Yeah. So feel free to maybe raise your hand and ask questions that way. So yeah, I guess then in that case, you will not see the link to the GitHub that I put in the chat. So I will just show you kind of on the screen. It should be pretty easy to type this in. If you go to this repo here, so it'd be github.com/LEDDL/AutoML-fall-school-2022. That's where you're going to get the code for today. So I'll give everybody a minute or two to get there. And maybe while you're doing that, I will just kind of give sort of an oral introduction to what H2O is. I don't know if there's any way I can see like one of the rooms here. I can't see like the other one, but it was on there for a minute. But I was going to ask for like a show of hands. How many people have actually heard of H2O or used H2O before? But yeah, I can't really see anybody. So I'm just gonna assume that some fraction of you have heard of H2O and some fraction have not. So just for those of you who are not familiar with H2O, it's a machine learning library for tabular data. So very similar to like a scikit-learn type of library. Definitely fewer algorithms than scikit-learn. It's more focused on scalable machine learning algorithms. So we don't have every single algorithm under the sun, but we have pretty much all the main ones that people like to use these days. You know, random forest, gradient boosting machines. We have XGBoost actually also bundled into H2O, which is one of the only algorithms that we have in there that's not written by us. You know, GLM, deep learning, some basic deep learning, not something that you would, not the extent of deep learning that you would find in like a TensorFlow or Torch, but just some basic multi-layer perceptrons for tabular data. We have stacked ensembles, we have AutoML, we have a number of unsupervised algorithms, just a whole bunch of stuff that you would, you know, find useful. And kind of the goal of H2O, like why does it exist if we have scikit-learn is a valid question. So I think one of the reasons that it was created a long time ago, it's been around for about 10 years now, was because it's meant to be a scalable machine learning library. And that if you can remember, I don't know how many of you were working in machine learning or AI back 10 years ago, but that was kind of the era of quote unquote big data, where everybody was really concerned about big data. And I don't know if people are as concerned about it anymore, or if it's just kind of assumed, but H2O was designed to be a library that could scale to like large data sets with large number of rows. So so it's a distributed system, and but it functions just sort of like a normal Python or R library. There's also an R interface. I'm not going to be going over that today because I figured most people here are probably more Python people. I could be wrong, but if you're interested in using it from R, you can download the R package from CRAN. It's called H2O. It's very similar. We have all the same algorithms because all the code is written in Java underneath, and then we expose that code to the R and Python client. So everything is the same in the two interfaces. And basically the only requirement to get H2O running on your machine is Java. So that is something that you will need to have running on your machine. And if you're not sure, like a lot of people might just have it already. I'm just going to show you maybe how to check on your machine if you have it. So, oops, I want to make this bigger so you can all see it. I don't know how big it is up on the screen in there, but let's see here. So if you just type in Java-version, you'll see something hopefully come up. And if not, then you do have to download Java. So I'll just take a minute to show you how to do that if you don't have it. Another thing that I'll do is point you to this web page, which is the H2O documentation. Let me just show you how to get there in case but it's probably impossible to see the URL on the screen. So if you just type in docs.h2o.ai, that brings you to this page. This is a general documentation page. It has stuff for like all of the, yeah.
Could you increase your font size or something, or you don't really see? Yeah.
Is that better?
Well, now we see that, but if you type something up in the bar, we don't see it. So
yeah, maybe
like
I'll just
on the previous page up there, we don't see.
Let me just open up like a notepad that I can stick things in, which will be big.
Great, thank you.
Mm-hmm. Okay. So what I'm telling you to do first is just go to this first URL, docs.h2o.ai, and that'll bring you to this page that has all the documentation for all of the different products that we have. And just some background, like I would say around half of these products are open source and half are not. So you're probably more interested in the open source ones. So that would be H2O3, that's what we call H2O. H2O Wave is a like an app development. It's kind of like Streamlit a little bit if you're familiar. But I'll just point that out. So we'll go down here. If you click on that, I'm just kind of showing you how to find this if you get lost, because it's a little bit easier to remember docs.h2o.ai than the actual URL. So then you just click there. So this is really what you want, like for anything to do with H2O. Here's the AutoML section, which is what we're going to be going through. But let's see here. This would just show you how to download it. So basically, here's some requirements. Pretty basic. So my point in doing this is to for those of you who do not have Java on your machine, you would want to go ahead and click here to get it. You can you don't need to use like the Oracle Java. If you have Linux, you can just download OpenJDK. That also works. So I won't go through that whole step. So if you are wanting to do that, please go ahead and do it. And then maybe you'll be like a little bit behind because we'll just kind of assume that you can do this. The next thing would be just downloading the H2O package. So this is just a Python package that you can pip install. Pip install H2O is how you do it. Let's see here. Let me go back to, I'll put this link up here too. So this is the GitHub repo, and I'm going to make this bigger. So you'll find everything that you need in here. If you want to use a virtual machine, you can. If not, like you can just click on this requirements.txt to see what the requirements are, which are, there's a handful. These three here are requirements for H2O. The request module, tabulate, and future. We're going to be doing some plotting, so you don't have to install matplotlib to use H2O, but we will be using the plotting functionality, so that would also be good to have. And then of course H2O. So, and if you want to just, if you want to just go ahead and, I mean, it's up to you. I tend to like create new environments when I'm working with Python projects. So if you want to do that, this is kind of how to do that. You probably already know, but if not, feel free to copy paste this. And I'll give everybody another minute or so to kind of get that installed if they want. But I'm going to be going through the notebook, so you know, if you just want to watch, that's cool too. Okay. So the notebook is right here, and I'm going to go ahead and actually bring it up on my machine. Okay, let's do that. Okay, so just like before we get started, let me just tell you what we're going to do. So let me go back to this. So I have two notebooks actually. So one of them is this one here. This is just kind of like a basic classification notebook. So just we have a binary classification data set, and we're gonna train the AutoML function, and then we'll get a bunch of models back and we'll kind of look at them. We won't go into like too much detail there. And then we'll have another notebook, which is here. This is just separately. I didn't want to recreate it because it's already fine. So this is also this one is related to explainability. So we're going to do like some. I'll show you how to basically use the sort of automatic explainability functionality in H2O, like that you can use with AutoML. And then if we have time, I'm going to show you something new that we're working on. We'll see how it goes. And yeah, well, okay, so let's get started. All right, so let's see, what do we do first? So we import H2O. H2O AutoML is the name of the function that we need, and we'll just go ahead and import that. And one thing that we do at the beginning of any H2O script is we what we call initialize the H2O cluster. So if you can remember from before when I was mentioning that all the algorithms are written in Java, and that's why we have to use Java. Basically how it works is H2O runs as a Java process. So that's what we call the H2O cluster. And that can be run locally on your laptop. It can be run like on Amazon or some cloud service. It can be run anywhere, but by default, it will just like start up on your laptop if that's where you're running the code. And basically, yeah, it's just a Java process. And to use H2O, most people would use like the Python or the R API. So what that does is that's just basically an interface to the Java code on the back end. So we just have this concept of like starting an H2O cluster. That's where all the like, you know, stuff happens. It's a little bit like Spark. So Spark came out about a year or so after H2O, maybe a year or two after H2O. And the whole concept of Spark is very similar to H2O. We have our own like distributed data frames. We have our own sort of like cluster. So a lot of the same concepts, if you're familiar with Spark, like kind of apply here. So that's just one way to think about it. So what I'm going to do is just go ahead and run this. And then what it will do is it will look to see if there's like an existing H2O cluster running. There are parameters to this H2O init function. So one of them is the IP address, and another is the port. So by default, it's going to run at localhost and then port 54321. It runs as like a web server. That's how you connect to it. So when you're typing in all the code in Python, it actually converts that to REST calls and then sends it like over REST to the H2O server. So that's why you can connect to it that way. So I actually already, you know, have this running because I, of course, ran the code before the workshop just to make sure everything was working. And what we see here is just some output like that might be helpful. The version number. Let me make this a little bit bigger again. Yeah, version number, a couple other things that are good to know. So one of the sort of things about H2O that's a little bit different from other libraries is it has like very specific memory management. So as the user, you are sort of in charge of that. So you're in charge of saying, you know, I want to allow H2O to use this much memory on my machine. This is a little bit different than like running something in like a typical machine learning library in R or Python, which is just going to take up all your memory that you have. I mean, there are some, I think, certain packages that you can specify this, but for the most part, in general, when you run like machine learning code in R Python, it just kind of like uses all the memory that's available on your machine. In H2O, we're like a little bit more specific about that, and we allow you to, you know, put a limit on that. Everything has defaults, so some of the stuff like you don't actually have to think about. By default, if you're running like on a laptop, it will just take 4 gigs of memory, which is you know, most laptops have 4 gigs, so that's kind of why we choose that. But if you start to like work with very large data sets, the one that we're working with today, this is going to be like 20,000 rows, so it's like really small. We don't need to worry about stuff like memory really at this point. But if you had like a 1 gigabyte training set, you would start to have to think like, okay, is this computer big enough to train this model? Like, how much memory do I need? We do have kind of like a rule of thumb around this where for like a typical H2O algorithm, you might need like about between like, I would say probably like 4 times the amount of memory to run and train and do all of that as the size on disk. So if you had like a 1 gigabyte training file, you would need at least like 4 gigs of RAM. And that seems like a pretty good, you know, rule of thumb that works often. If you're running something like AutoML where you're training a whole bunch of models, you might need more than that. But I'm mentioning this stuff just so you know about it. It's really not something you have to worry about until you run up into like big data and like and basically H2O will just stop working and then you'll know. Okay, so a couple other things. Yeah, this is where we're connected, Python version. Yeah, so let's load some data. So we have this little bit boring data set. It's just predicting whether or not a product will be put on back order status. It's you can click on the link here. I think it's a Kaggle data set. But this is just a version of it we have hosted here. So basically there's some product metrics like current inventory, transit time, demand forecast, prior sales, and then you're trying to predict whether or not this thing is gonna go on back order anytime soon. So typical binary classification problem. This here is just like looking to see if you're running it in the repo, like if you started this notebook up where it exists, you can just load it from the repo. Otherwise, it's going to go out and find it. It's just going to grab it from the internet. Let's run that. So this h2o.import file is basically like our, pandas.read CSV. It's a little bit different. It reads the you can put CSV files in here. You can put like HDFS locations in here. You can put all sorts of data types in here. We're of course using a CSV because that's easy, but it supports quite a few different data formats, SVM Lite, other types of formats as well. Parquet files is one that we support that maybe some others don't. And it loads everything directly into the H2O cluster. So like nothing is actually in Python memory at this point, other than like sort of these pointers to the data set. So when you type in like the letters like df in Python, really all that is sort of a pointer to where the data exists in the Java cluster. But you can, play with it like it is a data set. So one of the things that we do in Python specifically is we try to have a lot of the data slicing and all of those types of things equivalent to what they are in pandas. So we don't support like 100% of all the pandas operations that you can do on a data set, but all of the like normal things that you would do, like slicing columns and all of, typical, very basic data processing, that's all the same syntax as if it were a pandas data frame. But in reality, what this is an H2O frame. This is something that is an H2O specific function. It's just a little function called describe, and it's going to show us the data. So we've got 19,000 rows, 23 columns. This is kind of what it looks like. Here are the columns on the top. We've got some sort of metrics about them. So what is the types, integer, min, mean, max, etc. Let's go over, see what else we have. So one thing I'll point out, so a couple different things to note are the data types. So we have integer, which obviously everybody knows what that is. We have a real number, which is slightly different than an integer, both numeric columns. And then this one is maybe something you don't know. It's called enum. That's just the name for like a categorical element in Java. So this would be like a categorical column. So that's just something to note. Enum means categorical. And all right. So, and then the thing that we're trying to predict is this column went on back order. So let's find that. It's a little bit hard to do it when it's this big. Okay, so here's the went on back order. And this is categorical, and we've got just like yeses and nos in there. Okay, so one thing in H2O that is slightly different than scikit-learn is that we have one function for each algorithm. So we would have like a random forest classifier. So in scikit-learn you have, or sorry, I shouldn't say random forest classifier. We have like a random forest estimator function, and that is both the classifier function and the regressor. So in scikit-learn, we have two different names. We have like random forest classifier, random forest estimator, or sorry, regressor, and you use, whichever one you're doing. If you're doing classification, you use the classifier one. If you're doing regression, you use the other one. In H2O, we just have one. And the way that you, sort of instruct H2O what you're trying to do, regression versus classification, is basically whatever the column type of the the outcome column is informs H2O what you're trying to do. So you need to have your data encoded in a specific way. So if you want to do classification, it has to be an enum type or categorical type. And if you want to do regression, it would have to be numeric, either integer or real. So that's just one other difference. That maybe takes a little bit of getting used to if you're used to just not thinking about data types. This is all sort of in the vein of like making this a very high performing system. It kind of forces the user to like use optimal data storage and stuff like that. So we don't have like different versions of the data where we like have to make a copy of it, etc. So I don't know if somebody had a question. I heard something. Is there a question? No? Okay. Okay, so next, so what else do we need to do? We need to, before we're ready to do AutoML, we just need to do a few things like, let's sort of identify what it is that we're trying to predict. Another difference from scikit-learn, and I keep referencing scikit-learn because I assume everybody pretty much knows the scikit-learn API. So we have, before I explain this thing up here, let me just show you the interface. So we've got like, this is sort of our, our machine learning method, like all of the H2O algorithms, including AutoML, have the same interface. So if you wanted to train a random forest, this would be called, random forest estimator. And then you would instantiate the class here. So you make an object. We're just going to call that AML, AutoML, and then you put some of the arguments in there. So I won't go into that yet, but let me just show you like the data interface. So if you're using scikit-learn, we would have like, object.fit, and then X would be the data, the training data, Y would be the response column, and then you would go ahead and train. This is a little bit different. So we have 3 pieces here. So training frame is the actual data frame, which would include X and Y together. And then the way that you specify like which are the predictors and which are the outcome are just these small x, small y. And one of the reasons that we did that was so that you kind of just have one data frame here. It's just, you're always working with the same one. If you want to change the columns that you're using to predict, it's very easy because you just change this X argument. So just slightly different here. So Y is the name of the response column. It can also be the index if you want to use indices. And then X, what we're going to do here is we're going to grab all the columns first, and then we're just going to go ahead and let's remove Y because we don't obviously want that as a predictor. And then we're also going to remove this ID column, this SKU, because we don't need any IDs in our predictors. Not useful. So I think I clicked on that. And you'll see here the shape, we can just use that. So yeah, so this, I think it's actually, well, I already trained a model here. So I might go ahead, let me do something real quick. What I'm going to do actually is I'm going to shut down the H2O cluster and I'm going to restart it so that we can actually see what's happening. Well, actually, you know what? I won't do that because then we'll have to wait for it to train. So let me go back to this. So I'm just going to actually not click on this. It's going to take a few minutes. So one thing I'll just mention before we fake click on this is some of the arguments for AutoML. So there's kind of 2 ways that you can tell H2O AutoML how long you want it to run. So one way is that you can say how many models you'd like it to train. And then you don't really have any clue in advance how long that might take. But then you do know the number of models that you're going to get at the end. So that's one way. That's what we're doing here. Let me make this bigger again. So I'm just saying train 10 models. And one other thing to note before we move forward is, does somebody have a question? Okay. Is the max models. So let me just go ahead actually and jump back to this here. So just a quick description of what's actually going to happen is I'm getting a little bit of feedback. I don't know if somebody could maybe mute the AutoML Fall School Zoom, but okay, so what this is going to do is the algorithm essentially iterates over all the sort of useful algorithms that we have in H2O. So we have XGBoost. That's typically one of the algorithms that does the best on most data sets. It's not always the case, but there's a reason that we kind of went through the effort of putting that extra algorithm inside of H2O is because it's very good. Then we've got some GLMs. Those are just useful kind of for baselines, or if you want like interpretable models. We've got a random forest, and then H2O also has its own GBM algorithm, so that's different than XGBoost. It gets similar performance. It does better in some cases and worse in other cases, depending on the data. So it also sort of is parallelized and distributed in a different way. So it can be better for certain size data sets versus XGBoost, et cetera. So we have some of those as well. We have a deep neural net, an extremely randomized tree forest. Then we move on, and I'm doing these actually in the order of how we do it. Then we move on to like actually training random grids of these things. So the goal is to kind of like quickly train like kind of a diverse assortment of different models, get some good coverage there. And then we move on to sort of like more grid searching, and we go into a random grid of XGBoost, random grid of H2O GBM, random grid of deep neural nets. And it's a little like, I'm a little bit simplifying what we do. There's like a lot of other things that are kind of happening to organize like how much time is getting spent on each algorithm. That's kind of one of the more complicated things about the algorithm is figuring out like, okay, the user gave us, this much time, how much time do we want to spend on this versus that versus that? We want to kind of be efficient with our time. So if we, if the user gives us like 3 hours, we might do something different than if they gave us 10 minutes. And another thing that happens throughout the process is so we have actually these things that we call like model groups. So kind of each of these little steps that I've gone through is like on the back end, a concept we have called model groups. And after each group, we actually train a stacked ensemble on the set of models that are there at that moment. We used to have the algorithm used to be such that it would train all the base models, and then at the end it would train like 2 different stacked ensembles. But I don't know, in the last year changed it so that we're getting stacked ensembles as you go. It creates more diversity as well. Like some of the stacked ensembles kind of, so one of the things about stacked ensembles, if you're not familiar, is like, it depends on, how many models you have, but if you have like 100 models and you have a stacked ensemble with 100 models in it, it's maybe not the best algorithm that you would want to use in production, because when you're scoring, a stacked ensemble, it has to score 100 models, then feed that output into the stacked model, and then you get the output. So one of the things that H2O is like with this whole, software is designed for, enterprise use and business use. So we're always thinking about like scoring speed and things like that. So in a lot of cases, you don't care about that and it doesn't matter. But one of the things, or one of the reasons that we added these extra stacked ensembles in there is to have more like smaller ensembles. So that, you have a good variety of like smaller ensembles that can be used that still get really good performance, but are like much faster in the scoring step. We will train a stacked ensemble at the end that has like all the models in it. And often that is the best model. So it just depends like what your use case is, like what you care about. If you want just ultimate like model performance, usually the stacked ensemble with all the models in it is the winner. But we want to give you some options. So yeah, we as the process is going, we iteratively like train stacked ensembles, and then at the end you have some series of base models and then a bunch of stacked ensembles. Okay, so and maybe one thing else that I'll mention here, you have some control as the user over what the AutoML process does. So this, of course, is what I'm talking about, the default behavior. And if you want to turn off certain algorithms, you can do that. We have like something called exclude algos. We also have include algos if you want to specify it that way. Like, let's say you don't want any deep neural nets, so you want to turn that off, or you don't want any GLMs. Or maybe you just want to use H2O AutoML to be sort of a tuning function for XGBoost. Then you can say, just train XGBoost. I don't care about anything else. And then AutoML will just focus on XGBoost and tuning that. So there's a couple different ways that you can use it, but it will use all the algorithms by default unless you tell it not to. Okay, so back to the code. Let's see. Yeah. So the reason I got kind of down that path is max models refers to just the number of base models. It does not include the stacked ensembles. So that's just a note. So you're basically saying train 10 base models and then however many stacked ensembles get sort of peppered in there. Setting a seed, you know, sometimes good to do that if you want. One note about reproducibility is that all the H2O algorithms are reproducible with the exception of the deep learning. The deep learning algorithm can be made reproducible if you reduce the computation to one core, but then it's much slower. The deep learning algorithm uses a technique called hog wild, which is like, it's a not reproducible thing. So like it's very fast underneath, but not reproducible. So one of the things to note is if you do use the seed and you do have deep learning enabled, it will be slightly, you know, different each time. So if reproducibility is important, I would just go ahead and maybe turn off deep learning. You could check and see if it's doing well or not, but that's just one thing to note. Okay, so and the other thing that you can do is, so I mentioned there's two ways to train H2O. One is max models. The other is just max runtime, basically. So there's a, let me go here. Let me make this big. Whoa, too big. Okay, so yeah, so the other the other option is max runtime seconds. So it's just the number of seconds that it can run for. And this is pretty precise. We spent like a whole year trying to get it like very precise so that it would behave exactly how we wanted. So because that also includes all the stacked ensembles and stuff like that. So we have to like sort of predict in advance like how much time that's going to take, and like we want to make sure it's behaving properly. That was important for benchmarking. So yeah, you can just use it however you like. Another note is like if you use max runtime seconds, it's probably not going to be reproducible because like whatever sort of amount of resources you have on your machine at a given time might be different. Like if you run it again, maybe you're running some other stuff and then it has more compute to like do more models. It, you know, is not necessarily going to be reproducible. So basically we run that. If you've been, I guess I should have said, if you want to follow along, you should probably click to run that before I went into like a 10-minute discussion about it. But basically it, hold on a second, do this. There's a little progress bar, which is kind of helpful. So it will kind of show you how your progress is. And I think this one runs for, I don't know, a few minutes maybe. Then it's going to spit out some stuff, which I don't think is super helpful. So I'm going to skip over that. It's just showing the metrics for the best model. Okay, so then the main thing that we do to sort of evaluate the AutoML is look at the leaderboard. So the leaderboard is kind of just what it sounds like. It's a data frame that ranks all the models based on their performance. And that's stored here. The AML object is the AutoML object, AML.leaderboard. So it's just an H2O frame. So we can kind of take a look at it here. Let me make that slightly smaller. So what we have in the leaderboard is we have model ID. So this is how we identify the different models in the run. So typically they have just the type of model as the first part of the string, and then just some date, basically, like I ran this today. So that's the date. And what we see here is this was a very short run. So in fact, we actually are not getting a whole bunch of extra stacked ensembles. So what we have, actually, let me scroll down and see. No, we don't have any extra stacked ensembles. So like I said before, some of the, this goes into just, it's gonna be kind of different depending on how much compute you request. This one was a very small run. So we didn't, basically, we chose to, and this is just part of the algorithm, how it works. We chose to kind of like preference training more base models over like a lot of stacked ensembles. When you only have like 10 models, it's not that useful to have like 5 different stacked ensembles. So, so it changes basically. And it's sort of trying to be optimal for whatever time you give it. So what do we see here? We see model, we see some model metrics. So this is binary classification. So we have some binary classification metrics like AUC, log loss, the AUC under the precision recall curve, mean per class error, RMSE and MSE. These are all 5-fold cross-validated metrics. So in the background, what's happening is it doesn't just train 1 GBM, it trains by default 5 does 5-fold cross-validation, trains 5 GBMs, averages the metrics, and that's what you get here. You can change that as well. Of course, lots of things are configurable. If you want to score the leaderboard on like a specific frame, like let's say you have, some holdout frame that you want to get the metrics on, there's an argument called leaderboard frame in the AutoML train method, and you would just give it that frame. But by default, it's going to do 5-fold cross-validation and give you those metrics. One of the reasons that we do cross-validation and sort of like waste the time to do that is because it's very helpful for the stacked ensemble. So that's, you can do stacking without cross-validation. You can score the base models on a holdout frame and then build the stacked model on top of that. However, you do get better performance if it's cross-validated predictions. So that's why we do that by default. But again, like depending on your needs and your preferences, you could tweak all of this. You could say use a holdout frame for the stacked ensemble. Don't do cross-validation. You can tweak everything basically in the algorithm. So yeah, what do we see here? A couple GBMs doing best, XGBoost down here, a couple more XGBoosts. The XRT is extremely randomized trees. In H2O, if you do head, it just gives you the top 10 rows to print out. So let's scroll down. Let's go ahead and see all the rows. So in head, we have a rows argument. You can just say leaderboard. And then this is just, a frame, so you can do n rows, and you can actually see the whole thing. So now we have a couple extra things here. We have DRF stands for distributed random forest, and then GLM. So it kind of looks like what you might think, GLM, not doing so well at the bottom here with 0.75 AUC. And then we jump up to like a 0.93 here. We're getting into the 0.94s. And then you can see there's a difference between if what you have is the just base models and if you have a stacked ensemble. So we're jumping from, let's say 0.948 to 0.949 to 0.952. And that could be significant depending on what your use case is. So, and you can kind of see a slight difference between the two models here. So I didn't explain this yet. So the stacked ensemble all models is kind of exactly what it sounds like. It's a stacked ensemble from all the base models. So it would have, 1, 2, 3, 4, 10 models here. The best of family, this is one that we created that's sort of optimized for production use cases. So essentially what it does is it just takes the best out of each algorithm class. So it will take the best GBM, the best XGBoost, the best XRT, DRF, best GLM, and forms kind of a smaller ensemble. I think there's about 6 models in there. So it'll always be that same number. And so a little bit more predictable. And if you wanted to have kind of a faster model to use in production, it's still a stacked model, you can do that. And this, here, a stacked ensemble with 6 models versus 10, there's not a big difference. But if you had several hundred models or 1,000 models or whatever, there would be a big difference. Okay. Any questions from the audience right now? Okay. So one other thing I'll point out, so we have this leaderboard here, and so far we've just seen like there's model metrics on it, which are useful, but there might be other metrics that you care about, especially if you're kind of making models for production use cases. So, so we have this other method here. If you do h2o.automl get leaderboard, you tell it, give it your AutoML object, and you can just say, give me all the extra columns. Then we'll generate some new columns for you, and you'll see the old ones there, but here's a couple more that are nice to have. We have training time. So that's just, you might care about that. I don't, it depends on your use case. You can see here that these are all quite different. Actually, they're not that different in this case. They're all like relatively similar. So that's milliseconds. Another thing you might care about is predict speed. So this is really important if you're productionizing your models. So, and you'll see that like, well, let's see, this particular example, there's really not a big difference here between the base models. That's not always the case. Sometimes some of the models just, especially if you start getting in, like you run it for a long enough time that you start getting into a whole bunch of random grids and you're getting like very deep trees or things like that, you might get like really good models. It might be even like the best base model might be something like really deep, but then maybe it's very, very slow to make predictions. So you might not want to use that. So this is like something to use if you're kind of just wanting to kind of pick and choose what model you might want to take to production or use for some other case. So that can be useful. So one thing that I'll just show here, this is new in the latest version of H2O, is we have a Pareto front that can be applied to the AutoML object. And why do we have this? Well, for kind of this reason that I was just talking about is like, let's say you have all these models, like you don't really know how to choose them all. Like maybe some of them are like, some group of them are all like similar in terms of their model performance. This will give you a little bit more of a, like, let me make this smaller. Oops. Can get it all on one screen. Okay, so this I found to be useful. Like if you're trying to say like, I want the best model, but I want it to be also fast in production, like scoring. And then what we can do is make a Pareto front and we compare, this is per row prediction time in milliseconds on the x-axis, and we have just model performance in terms of AUC on the y-axis. And then what it's going to do here is it's going to draw this Pareto front, and you can kind of start to see how different models perform as well. You're seeing in purple here, like stacked ensemble. These are the 2 stacked ensemble models. These are taking more time to predict, and you get like a little bit of performance for that, and that might be worth it or it might not be. Then you can look here, we got like a GBM, which is like doing pretty well. Like that might be a good model. Or, you know, if you want something really, really fast, you might have this XGBoost here in brown. You know, also these are very small times. So like it just completely depends on your use case. This looks like it's a huge difference, but it might not actually be meaningful for what you're doing. So there's other things you can compare by training time as well. So that's just kind of a handy thing. And so now that you like have all these models, you know, you did all this work to train them, so they're all like available to use. They're just sitting in the H2O cluster. And if you want to kind of look at them or examine them further, here's just a couple of the functions that will let you do that. This is how you would get like the leader model. We store that in aml.leader. We have another function that's sort of a multi-use like utility function. So get best model. So this will, you can get the best model based on different things. So if you want to say, give me the best model based on log loss, because as you noted above, like the leaderboard is ranked by default AUC. So unless you tell it otherwise, there's all sorts of, again, like options in the H2O AutoML function that you could say like sort metric equals RMSE or log loss if you want it to sort by something else. Of course, it's also data frame. You can resort it afterwards if you like, but it will just try to store one version of the leaderboard and whatever, and it'll be ranked in sort of the default way, unless you tell it otherwise. So if you want to just kind of have this handy function to grab things by different metrics, so you can say also like get the best XGBoost model. So you can say by algorithm. So criterion would be the metric, algorithm. You can do both as well. So that just can be kind of useful to grab things quickly. The other way to get models is by their ID. So we have like an h2o.getModel function. And what I mean by like get the model is I mean just putting it in a object in Python that you can then access and do things with. You can plot, you can look at the hyperparameters, you can do whatever you want. So here above we get this XGBoost, and we might look at this actually not printing out, but like if you want to see all the parameters for the XGBoost model, and if you want to also inspect specific parameters, so let's say we want to look at entries. So what we see here, there's 3, so entries, you might think, okay, that's going to be an integer. It's actually a dictionary, and in it we have the default value for entries. We have the actual value that it found after doing early stopping. So it's this is part of the training process. The input, we said, you know, you can have as many as 10,000 trees, and as part of the you know, tuning process in AutoML, it actually like found the optimal to be 54. That's a little bit low, but you can also tweak the tuning, the sort of early stopping parameters. So that's another thing. Let me just show that to you real quick. So this is something that all the H2O algorithms have, like some subset of the algorithms have early stopping, like GBMs and deep learning, et cetera, XGBoost. So there's different ways to control that. We have some defaults in there. So maybe you'll find they're too sensitive or not sensitive enough. So that's another way you can like debug some of the models that we train. So if you're finding, let's say, you don't think the trees are deep enough, you can tweak this to be like less sensitive and they'll stop later. So we have a couple of ways to do that. Stopping metric, you can you can actually specify, like, I would actually like you to do early stopping based on, some other metric like log loss versus AUC. Then we have the stopping tolerance. That's just basically how sensitive it is to stopping early. So you just kind of push that number up or down if it's, too sensitive or not sensitive enough. And then this is another way that you can control that as well with the stopping rounds. Okay, so back here, let me check the time. Okay. And then this is the last thing of this notebook. We have something, there's different ways to save these models. So again, this is going to be H2O specific because we have kind of our own way of doing this. So one way is you just use the save model function, and this is what we call like this sort of like a binary format. It's just, if this is just, you're just kind of playing around, you want to just save your models for later, you might just use this. One note about the binary format is that these models are tied to a version of H2O. So if you train them in, 338.0.1, you need to like load them back into that version. So that's a limitation, which is, significant. So if that's a problem for you, you might consider doing this other format, which is called the Mojo. This stands for like model optimized Java object. This is sort of the format in which we recommend if you're going to production with the models. It's another kind of like binary format, but just slightly different, and it's also not version dependent. So if you want to just save a model and like maybe you want to use it a year from now, probably just use the Mojo because it'll always load back into H2O. It's a little bit of a stripped down version. It's optimized for scoring. You might not have like all the every single metric that you could have about a model, but it has most of the stuff that you need, and you can load it back in. So those are just kind of the two things there. Okay, so that's like a basic kind of introduction to H2O AutoML, and I just want to go ahead and kind of, before we move on to the next thing, kind of show you the user guide, because this is really where everything is. And let me bring up my thing here. So that's actually this link here, docs.h2o.ai/H2O, and then all of our docs are versioned because things change over time, but this is kind of the generic one that's going to point you to the latest version of H2O. Okay, so yeah, so just wanted to point you here because this is basically where everything is that you would ever want to know about H2O, and there's like links to other tutorials and things like that. Also, it's in the H2O user guide, so anything else, any other questions that you have about H2O, you can find here. Like if you want to say like, what algorithms are in H2O, like here's a list. A bunch of things that we didn't talk about, isotonic regression, Cox proportional hazard. So lots of more like statistical things, unsupervised stuff. Yeah, like this can be used to do like collaborative filtering, like recommendation systems. Yeah, PCA, isolation forest is good for anomaly detection, things like that. And then a couple other things, miscellaneous. Target encoding is not necessarily like an algorithm. It's just a pre-processing step that can be very useful if you have categorical data. And anyone who's sort of done Kaggle before or like tried to win Kaggle, this is one of the techniques that is often used to process the data as target encoding. TF-IDF if you have text data, Word2Vec if you have text data. And then permutation variable importance, I guess that's listed here. All the H2O algorithms, aside from stacked ensembles have some internal variable importance already, but we also have like an additional type of variable importance, which is the permutation variable importance here if you need something different. And then here's like how to train the models, cross-validation, checkpointing. That's useful. Like if you, I don't know, have big data and you want to like save a model and then like train more later, things like that. This model explainability is what we're going to talk about next. But let's just go back to here so we can kind of point out some of the useful things that I might have missed in my tutorial. So here's all the parameters for H2O AutoML. A lot of these are the same as like any algorithm in H2O. They'll just be different. So project name might be useful. I'm going to make this a little bit bigger again. Project name is an AutoML specific parameter. It's just like if you wanted to create multiple like instances of AutoML, like in your session, like if you want to have one leaderboard for something and another leaderboard for something else, you can use project name to kind of tell AutoML, like on this data set, I want like to train like one thing here and then, you know, another thing here. It's also useful if you want to, so one of the sort of workflows that you might choose to do with AutoML is like you might train like a little bit, but let's say you want to train like 20 models first, just to kind of see where you're at. So you do that. And then if you want to then restart the AutoML process, you can specify project name, which if you say, like it'll generate like a default project name if you don't specify it. So let's say you train 20 models and then you get this AutoML project, has a name, an ID, and then you want to train like another 50 models. Then you just say AutoML again and say project name equals the name of the existing one, and it will just add the models to the leaderboard, and it will also not like repeat some of the stuff that it's already done. So that can be useful just sort of as a way to use it. I already mentioned the exclude algos and include algos. This is a little bit maybe too technical, but this is, you can kind of reorder the steps of the AutoML process if you like. I don't necessarily recommend doing that, but it's something you can play around with. We have some pre-processing steps. So all the algorithms in H2O have some basic pre-processing to them. We automatically like handle categorical data for you. You don't have to think about it or like one hot encode it or anything like that. That's one of the, like actually one of the nicer features of H2O. When I start to play with another machine learning library, I remember that you have to do that. And I find it very useful that we do that by default. But there's extra things that you can do. This is experimental right now. We're kind of like working on trying to tune this better to make it like better, it's like just predictably good instead of like sometimes good. So you can tell it to do target encoding right now. There might be other things in the future. This exploitation ratio is another kind of like experimental thing where you can specify certain fraction of the budget to fine tuning the best XGBoost and GBM. Yeah, so like if you find like you're, you know, let's say you're not happy with the performance of the XGBoost and the GBM, you could like engage this parameter and give it some time to kind of more fine tune them. So yeah, monotone constraints, that's just kind of like not an AutoML specific thing. One thing I'll mention about memory, this is a little, you know, interesting because H2O has its own memory, which is all the, you know, the Java cluster, but then XGBoost is its own thing. So XGBoost is written in C++, it has its own memory management. So when you're using XGBoost inside of H2O, you just have to make sure there's enough RAM on your machine for XGBoost to be able to do its thing and also H2O to do its thing. So one of the sort of recommendations that we have are like if you're just using like the default h2o.init, you don't have to worry about this. But if you start to get into like really big data, or like you have very limited resources and you need to pay attention to this stuff, we just say like, don't let H2O use more than 2/3 of your RAM, because you want to leave at least 1/3 for XGBoost to have some space. I mentioned scikit-learn quite a bit. We also have a scikit-learn compatible API for the Python module. So basically we have H2O AutoML classifier, H2O AutoML regressor, and then we can use fit, predict, etc. There's a whole like notebook that shows how to do that. So if you already have like a scikit-learn pipeline or some scikit-learn code, you could potentially just change a couple import statements at the top of your script and start using H2O AutoML. So if you're interested in that, please click there. The next thing that I'll do is I'm going to talk about model explainability, because I think not a whole lot of AutoML tools have this, explainability built in so far. So that could be useful. And then just, here's, if you ever like just want to grab some code to start up, just go here. There's our Python. Just click between the two links. Okay. I didn't really talk about this, but if you want to like predict and generate predictions instead of just like scoring models, you can just use the predict function. This is talking about the leaderboard. Here's like an example of the leaderboard. Here's how we like look at the different models. So I copy pasted this code from here. Another thing that I'll mention, we have like a log of events. So like, what is H2O doing behind the scenes? We store that all in a log file. It basically will just say, training this, and then training that, and then training this algorithm, and then training that algorithm. So you can kind of see the whole process if you need some documentation about like, what did this do? So it's not really a black, like it's, I don't know, black box is a like weird term, but it's a black box, but there's some document that shows you actually what it did to get here. And just some FAQs, and let me just a note about GPUs. So H2O is like primarily a CPU based engine. If this goes back to, it was built 10 years ago, and that was the era of just starting to get a lot of cheap compute on Amazon and other cloud services like cheap CPUs. So everything's designed for CPUs and to be very fast on CPUs. However, we do have XGBoost in there, so XGBoost can use GPUs. So if you have a computer that has GPUs and CPUs, it can make use of that. So they need to be NVIDIA GPUs, and you need to have CUDA installed. But basically, yeah, the answer is you can, XGBoost can make use of that, and it can speed things up. One thing to note is if you don't see XGBoost models in your AutoML, that probably means you're running Windows. Unfortunately, we don't support XGBoost on Windows, and I'm not sure if we will anytime soon. So that can be, sad for people that are using Windows, because often XGBoost is getting, some of the best models there. If for some reason, it should be, available. You don't have to install XGBoost separately or anything like that, but if you need to make sure and check if it's available, you can do that here. Like if you're using Windows, it would say false. And then just some resources. There's some other tutorials, like the one that I went and created for today is based on like an older one that's linked here. There's a lot of slides. We have our roadmap. If you use it somewhere and you want to cite it, this is where you do that. And this gives very specific details about what our grid searches are, if you need to know. All right, and then, yeah, so we do our development on Jira, unfortunately, not GitHub, which is just so sad. But yeah, so if you want to create a ticket, if you find a bug, you go to Jira and you just make one there. And you don't have to, like, I don't think you have to create an account. I think you can just anonymously just click and, because I think I did that by accident the other day. You just say, bug project H2O, just, write your complaint in there. Okay, so I think that's pretty good coverage. So what I want to do next is go back to the GitHub and scroll down to the bottom. So we went over this notebook here. Next, we're going to quickly go through this explainability notebook. This is a link to the file. So you just want to maybe open up a shell and do wget and then this link. And let's see here. I have it already downloaded, so I'm going to go ahead and open that up. So we'll just go ahead and get this started. I think I'll try to make it a little bigger again. So this same notebook, before I go further, is linked here in the model explainability section of the user guide. It's right here. You got the Python notebook. There's an R notebook that is the same thing. And basically what I'm just going to do is show you some of the plots that you can get and might find them useful. So, okay, so we are having this wine data set. So the goal here is, this is a regression problem, and the goal is to predict wine quality score. So I don't know, somebody went out and asked people what they think about wine, rate it from 0 to 10 or 1 to 10 in terms of what you think the quality is. And then the predictors are things that are kind of like just attributes of the wine. So acidity, how much sugar is in there, how much pH, how much alcohol, etc. So we will do that. And actually, we're going to here split the frame into test and train. I think, see if maybe I'll run that. So run that for like 2 minutes. While that's running, I think this notebook is already has some stuff on it. So I'll just go ahead and walk you through. So we have this function here that's like aml.explain. So this explain method, it can, it's a method on the AutoML class, but it's also on any singular model. So if you train just, an XGBoost or random forest, you can do, whatever .explain, and it will also work. It will just give you a different subset of plots. So for AutoML, has AutoML specific plots in addition to like plots for the leader model, and you have to give it a test set. That's why I went ahead and created the train test split, because some of these methods require a holdout data set. So basically, it's going to take a little bit of time to run because the explain method actually creates all the functions. So if you look here back in the user guide, there is actually there's a whole bunch of what we call like explanations. These are all their own functions as well. So if you just wanted to get like a variable importance heat map plot, there's a function for that. The explain is just like a wrapper function that goes ahead and executes like all of them. Okay, so so basically, what are we going to do? We're going to click here. So the first thing it's going to do is it's going to give you a leaderboard, because that's like the main thing you might want from an AutoML object. And what we have here, like if you run it in a notebook, which I recommend you do because there are plots, and so it's nice to have them in a notebook. It'll tell you the name of the explanation. This one's called Leaderboard, and then it also gives like a little description. Sorry, we lost our thing here. A little description of what the explanation is. So it's just kind of like, here's a thing, and here's what this thing is showing you. So Leaderboard is a little bit, you know, obvious. So in this case, we've got 20 models. We trained 20 models in 2 minutes. So it's pretty fast. That is one of the other sort of benefits of using H2O. It's quite fast compared to other tools. And this is a regression problem. So we're going to get a residual analysis plot. This one actually looks a little bit weird because the data, you know, this is a regression problem. The scores are numeric, but they're not continuous. So it's just a score like 0, 1, 2, 3, 4. So that's why the residual plot looks a little choppy. If you're kind of used to seeing residual plots, they're a little bit more even. So we've got this. We've just got variable importance. So when we have an explanation that's really specific to one model, it'll just take like the leader model if that's appropriate. Sometimes it's a stacked ensemble and we don't have something like variable importance, so we show like the top base model. So this would be yeah, the top base model, which I guess surprisingly is a distributed random forest here, and we can just see what's going on. So one of the things that's kind of fun about this data set is that it turns out that the thing that is driving the score the most of all the things about the wine is the alcohol content. So basically people just like wine that has a lot of alcohol in it. It's what we learned from this exercise. And we'll go into that a little bit further. Like we can look at the partial dependence plots and see specifically kind of how that looks. So this, you know, simple variable importance. Then we've got a variable importance. I'm gonna make this smaller again. A heat map. So this is an AutoML specific thing. So we have on the bottom a bunch of the different models, and then we can kind of compare, you know, how each algorithm kind of evaluates variable importance, because each algorithm has its own way of doing that. So it's like viewing the, you know, it's consuming the features differently. It's using them differently based on each algorithm. So we kind of see some differences there. It can be useful for some things. Let's see. All right. Model correlation. This is just kind of more like in terms of choosing a model from the leaderboard, like how do each of these models kind of correlate with each other? Obviously, like there's not too much to be gained here. Like it's kind of just a nice plot. You can look at it if you want. So we have support for SHAP. So this is supported for all the tree-based algorithms. I think XGBoost, GBMs, and distributed random forests. So we can kind of see like so this is the SHAP summary plot. So with SHAP, you can have the contributions for a single row. So that's a super useful thing, and we'll get to that. But you can also just plot all the rows on a single plot and get kind of a global sense of like how each feature contributes to the outcome. You can see here like alcohol on the top. Partial dependence plots. This one is kind of interesting. So what we see here again is like, here's the alcohol content on the bottom. So we've got, you know, the lowest on the left and high alcohol on the right, and then the mean response on the y-axis. So this is the wine quality score. And basically, another thing is what you're seeing here is all these different lines are basically the top algorithm from each class. So we don't need to have everything plotted on here. We just kind of take one that represents each algorithm, and you can kind of see they're a little bit different. And let's, just kind of look at the general trend. So as the alcohol content goes up, so does the wine quality score, and it keeps going up and in a pretty linear fashion until about here. And then I guess people, don't care for more alcohol beyond that point, and it kind of tapers off. So it's kind of an interesting, thing to see if you're trying to learn kind of like about wine, so yeah, that's kind of what you'll see here. So it'll go through and it'll actually just automatically grab like the top 5 features, like based on variable importance, and plot the partial dependence plots for that. So that's volatile acidity. So more acidity is lower score. People do not like acidic wine. And then of course it kind of tapers off as well. Density, free sulfur oxide. So you can see there are some kind of trends here. You'll see this gray histogram in the background. What that is like, it's actually sort of a histogram of the density of the points in the data. So when you see it's big, that's actually like means there's more information informing that area of the plot. So if we go up, let's go back to the alcohol one. Like it might be the case that there's not a lot of data points up at these high alcohol scores. So that might be like, you might wonder a little bit about like what the plot is doing over there, because there's just not a lot of data. So that's just there to kind of give further information. There's something called ice plots, which is basically just it's like a partial dependence plot, but a little bit more specific. You can kind of go into like the different percentiles of things, whereas where the partial dependence is the average across all the different percentiles. You'll have to read more about ice plots if you want to learn further. So again, top 5 features. Oh, okay. And so then the next thing is, this is the other function that we have. So we've got explain underscore row. So this is if you want to explain specific rows, and then we get another set of features, or another set of explanations. So this is what the SHAP explanation plot looks like for a specific row, and it will actually have the values for that here. So we have like alcohol equals whatever value, and then the length there. And yeah, that's it. I think, I can't remember if it looks like we have not added the the Pareto front to this yet. We just released that, so that'll get added as well. I have a couple other things that I could talk about, but I want to know if anybody has any questions. I saw a hand. I think maybe somebody's going to ask a question.
No. What should I hear? Okay, can you hear me, Aaron?
Yep.
Okay, cool. I was wondering with the partial dependency plots, I think if I saw that correctly, you showed multiple models in a single plot with the explain function.
Yeah.
Is what's the reasoning behind that, to give the user a better understanding? Why not just show like the single model or like the final sample there?
Yeah, I think that's a good question. I don't know. I guess we just thought like it might be interesting to kind of see how they differ. Like most of the time, like they're not that different, but in some cases they are, and we thought maybe it would be useful to just kind of show, it's you can kind of see like the stacked ensemble is the leader model here. So it maybe one thing we could do is like make that line like a little bit bigger, like bold, so you kind of focus on that line. But there's you can also very easily see the partial dependence plots for any specific model that you want if you just use the partial dependence plot function. So this was just kind of geared towards model explainability in the context of looking at a lot of models at once, so that we kind of like stuck with that theme, I guess. But you can definitely plot it for a single one as well.
So I have a question. Thanks, Aaron. Can I directly comment on this? Oh yeah, go ahead. Oh yeah.
I don't know.
Aaron, can you hear me?
Yep.
Aaron, can you hear me?
Yeah, I can hear you.
Okay, yeah, if I'm just okay, yeah, if I'm just
I don't know. I probably shouldn't explain why H2O does certain things, but I mean, I can at least comment on why I would find something like this useful. I mean, there's this Rashomon effect, right? Where we know that sometimes we have quite a lot of models which have similar performance, but they reflect different internal structures of the data. And I guess as a user, I would like to see that. So if I'm lucky, like most of these well-performing models reflect the same effects, I have to worry, right? Because I can never really be sure. I mean, just by looking at something like loss and prediction error, which of these explanations are actually true, and you probably just don't want to kind of randomly pick the best one. So I guess that's a good kind of sensitivity analysis to show something like this. So I guess that would be my argument why I would like to see this as a user.
Thank you for that. If there are no more questions, I don't know if there are. I could.
Aaron, can you hear me?
Yep, I can.
Okay, cool. Sorry, because I'm uncertain how easy it is.
I'm uncertain how easy it is to hear me.
So yeah, I have a question. So you mentioned variable importance. So you say every model has its own way of doing that. Why do you choose to use model-specific implementations of variable importance rather than a generic version of variable importance? For example,
That's a good question. The answer is really just like time. Like it takes time to generate permutation importance, especially for a large number of models. So that's why we don't. So we already have it kind of like for free because we calculated it already for all the internal models. So if you want to do that, like actually it might be smart to add that as an option in the list of explanations and then maybe turn it off by default. But you can basically, you can still calculate variable or permutation importance for all the models, but there's just not like a one function way to do that. You just use it, if you go here, well, you just have to go to the permutation importance section and then see how to do that. So like that, but it's kind of a good question, and maybe we should just make a little function, utility function, to do that because it might be useful.
Awesome. Follow-up question I had, not necessarily follow up to that, but I have a question specifically about how you calculate rows per second inference speed. How do you calculate that?
So we just like it's let's see. I think we use the cross-validation, like we do cross-validation, so we calculate a bunch of rows at once, and then we just divide by the number of rows. So it's sort of an estimate, like based on the size of your data set. So there's going to be overhead like in any computation. So if you just calculated like one row alone, it would maybe be bigger than that amount. So this is just sort of averaged over all the rows.
Okay, gotcha. Yeah, I just mentioned this, yes, because basically the batch size of the data that you send to the visual will change the
Yeah, yeah.
Out of one that I keep in mind, we have like a batch size argument, right? For that. Yeah, it was cool to see like you have that for your frontier plot. It's really nice. Thank you.
Yeah. And yeah, we added that because we were doing it for, there's something called the AutoML benchmark, which is something that I helped create with a number of other people, some of whom might be in the room. It's just a benchmarking platform for benchmarking AutoML tools. And we have a paper that's hopefully going to be published soon in JMLR that will show a bunch of different plots and comparing different AutoML tools together with using these types of Pareto front plots with performance versus model performance versus prediction speed, et cetera. That's another place to explore that more. And I'm gonna just take 1 minute to mention something that we're working on. So if there's another question, I'm sorry about that. So I just wanted to tell you real quick about, we're making a new interface for AutoML, which is totally like web-based. I didn't go into like the existing web-based interface for AutoML, which actually does exist already, but we're building this one. It's actually mostly done with this tool called Wave, which is like an open source basically app creation engine. And I mentioned at the beginning, it's a little bit like Streamlit. It's underneath the hood, slightly different, but you basically can just easily make front ends for things. So we've been building a front end for H2O AutoML, and it's not out yet. It's like almost out. So, and I'm sorry we didn't have it for today, but basically what it is like all the stuff that you just saw is just in like a UI, and you can create data sets, or sorry, you can import data. You can basically like have this whole interface here, and there's nothing new here that's not already available in the Python API already, but it's just clicky. You just click through, you get all the visualizations, the model explanations, etc. And it's it can be it can just sort of speed up your process and make it more reproducible. So like, I don't know, I guess where to find this would be like, I'll post it on Twitter or something like that in like maybe a few weeks. And it will all be open source. Right now the repo is private, but it's built with, open source Wave, open source H2O, so it'll all be open source. And so if you're interested in kind of different UIs, kind of like keep your eye open for that. And I guess, yeah, my Twitter is @Liddell. If that's, I don't know how else to kind of communicate with this group other than through that. If there's some way I can send an email later, I would, or if there's like a Slack or something I can post to, but yeah, that should be out soon. And yeah, that's what we've been working on with my intern all summer. So I will leave it there.
Thank you very much, Erin.